Bob Bishop is the world-leading guru in this field. He is a guru who started with Silicon Graphics. He is the pivotal man in this visualization of huge amounts of spatial data. He earned his degree, by the way, at the University of Adelaide, and I'm very happy to hear that he's a mathematical physicist originally. Most of you will have heard of his role with Silicon Graphics. He's the International Centre for Earth Simulation former chair and CEO of Silicon Graphics. We need to set up his computer, so I might ask Bob to start making his way up to the podium, because we need to just plug it in and make sure that everything's working. There's quite a bit of technology going on at this conference. Thank you, Bob. So I'm just going to give you some bits and pieces, and then I will continue, so that as you can see, we have an incredible amount of bits and pieces floating around for this first session. So here is your power, Bob. And sorry, I'm tied up now, aren't I? We'll plug that in. And did you needed sound too, didn't you?
I did.
It's that plug there, which we can plug out of there. Apologies for the sound. So that was probably the clunkiest introduction to someone of this man's stature that I could possibly imagine. But Bob, thank you very much. We want to make sure that your technology is working, and I have to rearrange this again. Sorry. But ladies and gentlemen, would you please welcome the guru of why we are here, Mr. Bob Bishop. Dr. Bob Bishop. Thank you very much.
So what I like about this state, Queensland and Brisbane, is in fact that its attitude of moving forward in the technologies and tying the technology down to ground with the startups and the university academia environment and government. This combination of all three sectors of society collaborating very, very nicely. I had the privilege many years ago of installing many of the big supercomputers here, and I have to say it was a wonderful experience. But my bottom line of that was to convince the state that it should not be just looked upon as the sunshine state, but also as the supercomputing state. I'm not sure I made progress on that point, but the truth is it's now known as the smart state, and that's a good compromise. Now, I'm just puzzled why my machine doesn't come up here. All right, so the story, what Larry has painted as this picture of our planet and where it's going, it's so valuable and so useful. And I have to say, NASA is probably a global asset to everyone on the planet. It does so well at producing and capturing the key data. But the story is, I really want to go further and build on Larry's introduction, because it's a whole story from soil to sky and from space back to face. It's all those dimensions combined. Myself, when I retired from my day job, I've decided that to build a foundation, a private foundation based in Geneva, Switzerland, that was focused on exactly these issues. Totally neutral, totally independent, not for profit. I decided this is citizen science at its best. And the foundation adopted this strategy of just helping guide society through this great transition that we're now just beginning. And it's a result of the era of complexity, social complexity, but rapid climate change, and, as you know, very frequent national and natural disasters. So the way we're going about it is to build a virtual Earth just to better understand the real Earth. That's the reason to do it. It doesn't mean to say it's a substitute, but it just helps us create predictions about where the planet's heading. As you know, and you saw from Larry's slides, that we have a vast number of satellites up there already capturing data. In the ocean as well, we have thousands of buoys that are floating and sinking and then coming back to the surface and transmitting up to satellite and down to the ground stations more data. And this is very useful data, because the ocean is 70% of the planet's surface. So the ocean is, in fact, the 800-pound gorilla in the room that we have to come to grips with. And then we have all the supercomputers that integrate the data and do the analysis. This happens to be at NASA, at Ames Research Center in California, Mountain View, California. So the idea is how you come to grips mathematically with all the data and how you deal with the real world, which is massively complex. That's the key. It's massively complex. And the moon actually adds to the complexity and does some very good things for us as well to stabilize our planet. But the central issue is that all the processes, the biogeophysical processes, are co-evolving, and they're supplying feedback to each other, and they're synergistic to each other. And that's what makes the complexity very, very difficult to deal with. Even something simple like convection and cloud physics, we have not conquered these processes yet. We're on the way, but we haven't achieved a full knowledge of even the simple sky that we see on a daily basis, let alone to say the coastal zones, which have a great amount of non-linear complexity and play into our planetary picture. But overall, it's this integration of land, sea, and sky that we have to deal with, and the fluxes between those three units that make our climate, drive our climate. Models have got us a long way. This happens to be a very excellent model from Japan, known as NICAM. And here we can see the model helps us understand the flow of the atmosphere, the creation of storms, wind, rain. And we can track these models and look how they represent nature. And we can spend hours asking, what if this happens? What if that happens? Because this is a Japanese model, the focus was on the Pacific, and actually the genesis of cyclones and typhoons. Here's one that's emerging and heading towards Japan. But these models today do not give us a full understanding of reality. In fact, we are building, step by step, more comprehensive Earth system models. They are being built globally by many different countries and many different university units and government units. In fact, 61 of these models were recently brought together in what's called CMIP-5, which is part of the IPCC program. And, but even so, even with 61 models, we don't actually have a complete picture of the planet. But you can see here the evolution over the last 40 years of incremental scientific knowledge being injected into those models. But standing back, nature is borderless, seamless. Everything is connected. Everything is teleconnected. Everything is telecoupled. That's the bottom line. Now, how do we deal with that complexity? Well, Larry didn't show you this. This is a NASA simulation. And what's important here, aerosols are coupling the planet. Here's Sahara Desert sand blowing over to Central America. Here are the natural forests of the Amazon and Africa being coupled together with biota. Right blue down here is a transfer of sea salt spray. That's relatively harmless. But up here in the north, you actually have the gray transfer of, as you heard, carbon dioxide and other industrial pollutants across the industrial belt, North America, Europe, China, Japan, Korea. And of course, that's the most dangerous stuff. But there are other forms of coupling in this planet. And I point out that the combination of the monsoon and El Nino, these are both global phenomena. They are not local phenomena. They are global phenomena. And they couple the entire planet. We have to realize how important those two phenomena are. Here's the monsoon system. In the Asian summer monsoon, we've got the Indian Ocean creating the moisture which flows up over the Himalayas and creates the heavy rains in India primarily and China, which are just beginning right now. In the winter, the monsoon flows the opposite direction and brings cold Siberian dry air down over India and China and back to the Indian Ocean. But again, it's a global coupling. If we look at this simulation, it's from GFDL, which is a part of NOAA in the United States, and this is the sea salt, the sea salinity of the surface of the Indian Ocean. And you can see the Pacific Ocean flowing through Indonesia. It's called the Indonesian flow-through. And this coupling of the two oceans and the impact on salinity, as well as sea surface temperature, this is where we get the take-up, the vaporization and transfer of moisture into that monsoon system. Now, you may know that there is a global connection of our oceans. It's known as the ocean conveyor belt. It's driven by a combination of heat and salinity, and it couples all of our oceans on the planet. It also transfers water very deep down below the surface, and there are several simulations that we have of that coupling. But on the surface, above the deeper currents, we actually have the eddies. And the eddy system is another transfer mechanism. And here again is a NASA simulation showing the eddy currents of the planet transferring heat regionally. And these eddy currents are very critical for the fishing industry, for example, and any other analysis that we wish to do between the ocean and the atmosphere. A vast amount of heat being transferred here, fundamentally from the equatorial areas, poleward. You know, the nature has a tendency to simply distribute the heat, which is collected mostly in the equatorial area, and just distributing it as fast as it can to the cooler, colder areas. And as Larry pointed out as well, connected with all this, the temperature, the salinity, the currents, the eddies, is the underlying chlorophyll and phytoplankton source for the rest of the tree of life of the ocean. And so this is the coupling, the connection, the teleconnection. And we haven't quite figured it all out yet. We can see the pieces, but the issue is, can we bring it together in a holistic view? Larry showed the carbon dioxide. This is just a repeat of that. This is dangerous stuff because we know of global warming. And global warming is largely triggered by that CO2 emission, that blanket. And here is a 140-year forward simulation of precipitation and drought. We could watch this for 140 years, projecting forward. It's known as Project Athena in the United States. And of course, here's Australia getting worrisomely more dry, as is California and other parts of the planet. The bottom line of this simulation says what's wet gets wetter and what's dry gets drier. That's the simulation of the models we have looking forward for 140 years. It's a kind of worrisome projection, and it's largely driven by this CO2 accumulation that everyone is speaking about. Now, Larry also brought up the topic of Antarctica, and this is so key to Australia. If there is global warming and it continues, then we will see an accelerated melting of the glaciers in Antarctica. And this happens as the surface melt trickles down to the bottom of the glacier and lubricates the speed of the glacier as it flows to the oceans. So this perpetual accelerating glacier melt is quite worrisome. It's worrisome, of course, in the Antarctic and in Greenland as well. If the Antarctic were to fully melt, it would in fact raise sea levels more than 100 meters from where they are today. This is phenomenal. Of course, no one really expects that to happen, but that is a scenario. We have in Antarctic, in fact, 14 million square kilometers of continent, and we have it on average 2 kilometers thick. So that's what's at stake here if things were to really go bad. Larry mentioned the ozone hole. Luckily, the Montreal Protocol has capped the loss of ozone, and this is pretty much how it stands right now. But it's a 50-year cycle before this will cure itself, and the ozone will grow back, all things being equal. The protocol was signed in 1987, by the way, by all United Nations states. It's the only protocol that's ever been signed by all of the 196 UN members plus the EU. It's the only one, quite amazingly. The Arctic is, again, a polar area and is highly sensitive, and we're losing ice rather fast. But here's the consequence. We've found a coupling between the Arctic ice, because of albedo, the reflectivity of the color of the ice, into the polar jet stream. There's a link. And we're finding that the polar jet stream is destabilizing, and it's loosening up, and it's pulling further south and creating these tremendous cold, extreme winters in the northern hemisphere. North America, Eurasia, Europe, and it's rather scary because these events are creating, as in the last 3 years, in each of the last 3 years, 20,000 aircraft schedule cancellations per year. This is an enormous number of accidents to go with it. So it's fearful, and we're worried. And it just points out the connectivity of all of the Earth systems is the key issue. How are they connected? The bio-geophysical connection. What exactly is the underlying physics? Can we rely on it going forward? Are we interfering with it? What's society's link? And is there a positive feedback or a negative feedback loop going on here? Well, we can take this down to the city level, to the regional level. We can bring all those parameters down, what we call downscale our models to a city or regional plan. And this is where the rubber hits the road. This is where it's important. Half the world's population right now is in the cities. But if those cities are on a river, for example, like Brisbane, or by the ocean, as many of our big cities are, then any change in the river conditions, like extreme flooding into the floodplains, or in the case of a port, an ocean port, sea level rise, they will have to be taken now into consideration in planning. So the geospatial questions very rapidly transform from global to local. And by the way, they go back up again. We go from local back up to global because cities, with their emissions, for example, with their energy consumption, with their waste production, and with their heat island effect, those effects flow back up into the global model. So we have to upscale from the local city models back up into the global system to take account of how so many cities may affect the global system. So this is, again, how we conceptualize the idea of soil to sky and space to face. We've got to be thinking both ways. Sorry, this doesn't come out well, but it's a holistic view we're looking for. We're looking for that holistic, integrated view of society and physicality, all connected, everything interacting, and everything in motion. Nothing is stable, still, and permanent. And this is the global local picture we must find and we must develop. And in fact, this is the geospatial challenge. Luckily, we can do it today because of the vast amount of open data that's being collected and the visualization tools that make this transferable into a picture, a narrative that the public can understand and our decision makers can understand as well. And we can have a public-private dialogue very easily now than we couldn't really do before. Now, if you think that's the end of the story, you're wrong. It's a much bigger story than that. The whole solar system is interconnected, dynamically, continuously, and talking to itself. You know, of course, the sun is the main driving engine. It has all kinds of sunspots. We don't know the inner complexity of the sun, but we're finding it out. And there is an 11-year sunspot cycle that everyone, I think, is pretty much aware of. However, the sun is throwing toxic material towards the Earth at all times. And in the worst case, it's known as a coronal mass ejection. And these CMEs happen on a quite frequent basis. Luckily, the Earth is protected with a cocoon. Here's the Earth up here, and the cocoon is the magnetosphere of the Earth. And I'd just like to speak about that as well. Here's some data showing an actual CME from the sun in the center. Here's the Earth here, and Mercury, Venus, Mars are around us. But you can see how vigorous the sun can throw material at us. And it can be, of course, enormously damaging to our planet and to its environment, as it is to all the other planets. This happened to be taken in a week when I was in London, speaking in London in 2013, and this happened actually during exactly that same week. But here's our protection shield. It's the magnetosphere. It comes from the core of the Earth, and it goes way outwards for many hundreds of thousands of kilometers. But it's pinned to the Earth through north and south axes. And on the other hand, it's compressed as the Earth is heading in this direction. It's compressed at the front, and it has a tail at the back. This magnetosphere leaks. It is not a 100% defense shield. When the radiation ejections from the sun are strong enough, they will leak down through the north and south, and we get the aurora borealis in the north, aurora australis in the south. And in fact, last week, when I arrived here and switched on television, sure enough, because of a recent CME from the sun in the last week, there was the aurora australis was visible from the southern areas of Victoria. And I thought that was rather amazing. That's a perfect example of what happens when this magnetosphere of ours leaks. Now, when the leakage is strong enough, the ionosphere, which is about 100 kilometers up from the planet, conducts a vast amount of electric current. So we have these vast current fields flowing in our ionosphere. And through induction, those same currents flow on the surface of the Earth as well. So again, it's a form of coupling. If the coupling is too strong, we get a geomagnetic storm. In fact, in the northern areas like Quebec, this has already happened just 20 years ago. And it can happen again. If it happens more often, which it's likely to, the truth is we now live in an electric environment, electric society. All our GPS, all of our smartphones, et cetera, although the grid, the electric grid system, is vulnerable to this kind of blowout. And it's something we need to be aware of because the magnetosphere of the Earth happens to be weakening. And as it weakens, our cocoon, our defensive shield, will in fact allow more toxic material, radiation and particles to flow in down to the Earth's ionosphere. Now, inside of that magnetosphere, there are actually 3 Van Allen belts, which are toroidal shaped, and they collect a lot of very high energy particles. And we're just starting to learn about these 3 Van Allen belts that are inside the magnetosphere. So just what I want you to think, it's a simple thing. It's a very complex arrangement, and it varies dynamically from day to day. And this is the Van Allen belts moving around day to day and captured. Fortunately, we have the data now to capture and have the satellites to capture this data. And you can see the complexity of it. And this is just a portion of that magnetosphere that's helping us. Well, just last month in Australia, in the research centers of University of Sydney and the radio telescopes in Murchison on the West Coast, we discovered for the first time a visual insight into the magnetic lines of force and the plasma that builds in a tubular manner around those magnetic lines of force. This is quite a breakthrough, and it comes from Australia. It's delightful to see our science here being at the leading edge and putting these products out for the first time ever. And it was a vast field of radio telescopes, what's called a WMA, where we separated east and west and created binocular vision from a 3 by 3 kilometer array by dividing it in two and actually creating 2 different viewing points into space. And this is how these plasma tubes were detected. And of course, this has gained notoriety, and we're all starting to wonder the complexity of what's up there in the sky, the ionosphere, the Van Allen belts, the magnetosphere. My gosh, how do we bring it all together and understand and comprehend it and then look after it? Well, the story really begins at the core of the Earth. It's the outer core, which actually creates 95% of that magnetic field, the magnetosphere, not 100%. The crust of the Earth is a contributor as well because it has all the magnetic rocks in it. The ionosphere contributes also to the magnetosphere. So there's a lot to learn, and here is Europe, what I think is the most powerful program launched by the European Space Agency. 3 satellites together flying in formation, known as the SWARM project, and calibrating our geomagnetic field with the highest accuracy that's ever been calibrated. And this is just, again, this month, in the month of June, that data starts to flow out to the scientific community. Well, that's not the end of the story either, as big as that story is. Because if we come back and look at the crust of our planet, it's fragmented, and we have these tectonics that are transforming our planet surface on a daily basis. This is the earthquake occurrence around the world, mapped out, and as you can see, there are just thousands of earthquakes taking place every year. In fact, in the United States now, they're worried about the increased number of earthquakes, which are being driven by fracking and other oil, gas drilling procedures. So they're not shown here. This is just the natural earthquake systems. And relating to Australia, we are moving, as you know, northwards at about 4 centimeters a year. And we're part of this bigger system where India, Australia are on the same plate moving into the Tibetan Plateau, and the Tibetan Plateau is actually rotating clockwise in the midst of all that, and it's being pushed by the Pacific Plate and some other local plates. So you can see that this is a dynamic planet, and all of this is taking place just north of us. Here's a slightly bigger picture. It's fraught with earthquakes, and it will forever be fraught with earthquakes. We are lucky that we're in a relatively safe zone in Australia, but all around us, I think you know by the press, things look pretty bad. And here's Nepal just in April, and one big one in April and one in early May. And we all know the impact of this. I think about 9,000 people lost their life. But going back in time, here's Japan, what's called the Great East Japan Earthquake. The whole of Japan moved 5 meters to the east permanently, and 1 meter down. Now, this is China and Korea on a different scale. Actually, China moved 3.5 centimeters permanently. Now, this just tells you how dynamic our planet is. You think you talk about geospatial, you think you've got it nailed when you got the coordinates? Nuh-uh, no way. Everything is moving here. And of course, the destruction from that movement can be so bad that it knocked out, as you know, 3 nuclear reactors in Fukushima. And now the fear is Fukushima has been leaking for 4 years into the Pacific. What's it doing with pollution and the biosphere inside of the Pacific? How damaging can it be? Well, this is a list of all the big bad stuff that's happened over the last 10 years, including the activity in the Queensland. And I would just finish off by how important the planetary view is. This is the Ring of Fire, volcanic action. This is Cascadia in Pacific Northwest of the United States. Got 18 volcanoes connected to a subduction zone that are active. And what we have to understand is this triggering across specialization, across all the silos of the planet between the natural system and the social system. And this collapse is not going to stop because this happens to be underneath the Tibetan Plateau. We don't yet understand the inner core of the Earth and how it all moves. It is dynamic, it is not permanent, it's not stationary, it's in flux, it's plastic. And interconnected geospatial challenges require the interconnection of resources in our daily life and in science across our planet. So that's my bottom line. We're at the beginning here. This conference is at the beginning of bringing things together. Larry did a wonderful job of showing how important that data is from space, but data from the inner Earth is just as important. And then we've got to get down to the city. We've got to get down to the community. We've got to get down to where the rubber hits the road and where we live our life. But it's all connected. Thank you very much.